So what we are going to do in this module, which will run for maybe a couple of weeks, we are going to talk about object-oriented programming in C++. You may be familiar with certain notions of object-oriented programming, maybe at the surface or in depth. I really do not want to bombard you with a lot of theoretical notions. Rather, the approach that we would take is we would try to learn this language C++ or revisit this language C++ to know different features that it has, which enable you to perform object-oriented design and subsequent object-oriented programming. And the reason I'll first be talking about the language is the fact that this is true in any part of software engineering, that certainly you can be a good software engineer if you know your tools, because hardly few things can actually be done manually, and it's not preferred. Software engineering is the discipline, as we have discussed, of constructing software, and the processes that we follow must also be designed in a way, must also be followed in a way, so that the ensuring quality, ensuring productivity of the developer, that how much you can produce correctly in how much time, are very critical factors. And therefore, you need to have a lot of tools for every stage of software engineering. And it is critical that you know your tools very well and you can use them very effectively. So the first tool that we are going to talk about, it's kind of tool in a little different sense, is the programming language itself. The programming language gives you a lot of features, and you need to know how to use those features. Many a times, students or even industry professionals tell me that I know C++ very well. But then you look at the code that they produce, and you see that, well, it is written in C++, it is compiled by C++ compiler, but the style that the person has followed is purely procedural. There is no object notion, there is no proper formulation of inheritance mechanism, there is no right use of reference and all that. You have heard about many of these in the discussion that Professor Shorangshu was doing yesterday in the lab regarding Java. So that Java is also another tool that so your programming language is a tool, a very powerful tool that you have as a developer, which allows you to put down your thoughts in a concrete terms. So that it is the criticality of this tool is it converts the process in the mind into a very concrete document, very concrete formal structure, which can be machine represented and machine processed. So object orientation, or whatever paradigm we talk of, is equally between the design and the coding. It is not only in the design, it is not only in the coding. You must know how your tool, your programming language gives you features, and you must know how to use those features very effectively. So the discussion that we are going to take up, I will run through the whole of the C++ language, but not to give you very details of this is the right syntax. This syntax is how it is to be written and so on. I expect you to know that, or if you don't, you can learn that up, look up the book, or do tutorials and so on. But what I would try to explain more is why a feature. Why C++ does have this feature, which tells you situations in which that particular feature is of use. So that whenever you come across that similar situation in your life project, you will be able to rightly use your language. So I'll show you from the beginning itself in several cases with examples that what is a right way of using a feature or why a feature actually exists in C++. I'll often compare it with C also. And we will try to understand that why we have these features and how it is going to really enable us to do a better paradigm of programming, which is object oriented. And once we have covered the language and we know our tool, then I will in brief discuss about the overall object oriented analysis and design paradigm in brief. I hope that is okay with you. So before I start, we have 121 now. Before I start, I would expect that many of you would know C++, or at least you think you know C++. So those who know C++, would you please raise your hand so that I can get a feel of the familiarity that you have? Have everyone who knows C++ have raised your hand? Some more? Okay, good. So we have out of the 121 here, so let's say 120, we have about 69, nearly 70 people who know C++. So I will assume that you can lower your hands now. So I will assume that you have at least certain level of familiarity. You may have done some programming in this. Please lower hands. Yeah. And so that will help. But it is also, I have noted that there are about 50 people who do not feel that they know C++. So we will keep the discussion at that level. There's still one hand raised. Do you want to ask anything? Otherwise, just if you are just polling, then please lower it. Please lower the hand. Yeah. There's one still more. Okay. I think it was just. Okay, my next question is similar. How many of those of you who know Java, or you think you have a good idea of Java, would you please raise your hands? If you know Java, please raise your hand. Only 2, 3, 4, 5. If you know Java, please raise your hand. Are we done? Okay, we still not even 10. So very few people are familiar with Java. Please lower your hands. Thank you. Please lower the hands. Yeah. The third question is, how many of you know Python? Have used Python, written some programs in that? Okay. So about 54. Please lower your hands. You have a stronger familiarity with C++, more people, about 70, about 50, 55 on Python, and very few on Java. Though we will see that as we discuss, once you learn, say, C++ well, and you understand why the features are there, picking up on Java or Python would be very, very easy, because the concepts, the that the features have are very similar, because the concept is finally for translating your thoughts into the program. Okay, so with that introduction, let me please lower your hand, whoever you have raised. So with that, let me start the. Okay. So this is object-oriented programming in C++, this module. So broadly, these are the topics that we are going to discuss. First, what I'll discuss is what fascinates me quite a lot is C++ is not only, I mean, we look at C++ as an object-oriented language. So we are always talking about classes and inheritance and stuff like that. But C++ also it has very significant enhancement over C, which are purely procedural in nature. But they improve the programmability of the language, and many of them are needed for supporting the object orientation. So we will first talk about that, and then we'll go into classes, overloading, all those. Right. So while I will share this presentation, but I will extensively follow the I have a NPTEL course on programming in C++, which is a 20 hours video, each of about half an hour in 40 modules. And so you can, the links are given. So you can go to the NPTEL site on the link and watch those videos also if you need. And the module, that is the presentation on that is of these 40 modules, have already been uploaded in Moodle in terms of a Google Drive link. In addition, I also have another course in NPTEL, which is on object-oriented analysis and design. So it talks in depth about object-oriented approaches, which is also a 20-hour session. The link and modules are given. So if you want to go deeper into some aspects of object-oriented design, then you may make use of this particular course as well. So with that, let us start. I will stop this presentation and pick up the NPTEL presentation, which has been shared with you. So in the NPTEL presentation, I'm starting at module 6. First, one second. Let me share. Oh, I'm sharing the wrong file. Okay, I hope you can see this. This is module 6 in the NPTEL course. Module 1 to 5 it was actually a recap of C, on which I did not do a poll because I know all of you know that because you have done the PDS course. Okay, so here from this module, we will start discussing about what are the procedural enhancements that have been very useful in C++ over C. So it starts with the. So in this module, we'll talk about const-ness and inline function. So this is the module outlay. Let me just directly go. So you know that in C, you have been told that you can define something, a variable, as kind of a constant value or constant expression, and then use that variable so that whenever that variable features in the program, that value, which is given by the manifest constant hash define, will be used. And so that helps in multiple ways. Most significantly being that if you want to change that constant value, then you need to do change only at one place, whereas that value may have been used at 100 places in the program. Also, if like in pi, as you see, it is a big expression to get the actual value of pi, and by giving it a constant name, it really hash defined name really makes it easier to program. Now the question is, what is the core problem in terms of this style of programming? So the core problem is C programs, as you know, first grows through a preprocessor before it gets to the compiler. What the preprocessor does, it basically takes action on all the preprocessor derivatives, which are preprocessor directives, which are the hash directives like hash include, hash define, hash if def, and so on, and replaces all those by the corresponding action. So if you look at the output of the C preprocessor before the C compiler comes in, you see the program that you have written will look like what is shown on the right part. That is hash include IO stream, hash include CMath are replaced by the actual header text. So all those will be physically put there in the file. And then hash defines are also consumed. What it does, it knows that 2 is hash defined to the numeral 2, and TWO, wherever it sees in the program, it replaces it by the numeral 2. Similarly, it does that for pi. So you can see that for perimeter, we wrote 2 times pi times r, 2 pi r. That will actually become an expression like this. So I'm sorry. So what is the problem with that? The problem with that first is that the C compiler does not get to see the hash defined constants. So C compiler, so you see TWO in your code, but the C compiler does not see that. So when you debug the program, when you need to debug the program, it cannot show you what is the value of 2. So if you have a 100,000, 200,000 line code spread over maybe 40 files, you are really struggling, and probably hundreds of hash defines, you are really struggling to find out what is the value of that hash defined constant at a particular point is. So it necessarily slows down the debugging process. Each one of this point has to be looked at, keeping our final target of having better processes. So it makes debugging more difficult. So if it makes debugging more difficult, quality degrades, productivity gets less because you need to do more work. So the solution to that is to define const. So that is the reason you have const. So you prefix the variable declaration by a const, and then you initialize it with the value with which you wanted to do the hash define. So hash define n10 would now be written as const int n equal to or initialized as 10. So with that, your C preprocessor will not do anything. Compiler gets to know that n is a constant, and it preserves that variable, puts it in the symbol table. It is available in the debugger, and most importantly, it can check whether this const variable is being used with a proper type. With hash define, the compiler cannot check the type because it has just got a constant value there. So it has to just rely on that, whatever inference it can make from that constant value for the type. Whereas here, you are able to really declare what is the type, and the compiler will get to know that. And still you have a constant, in the sense that you cannot actually change this value of n after the const declaration. Doing something like n assign 5 will lead to a compilation error. If you try to do some smartness by doing indirection, then you can see that later part of the code, int m, int star p, which is initialized to 0. So these are all non-const. So P can hold the address of M, and by dereferencing, you can change the value of M. But you cannot do that for N. That is, neither you can directly make an assignment or change to N, nor you can indirectly do that. So because P is pointing to a constant value, whereas P has been declared to point to any kind of changeable value, right? So that's the basic notion of constness. So naturally, every constant variable must be initialized when defined, because you cannot change it subsequently. And of course, you can also have variable of any data type. Here I'm just showing a struct, complex struct. Variable of any data type can also be defined to be const. And if you define such a struct variable as a const, then no component of that structure can be changed. Everything will remain constant, right? So that is a basic notion. So if you compare here now the same program, what you get to see is using const, there is no replacement by CPP. So it is const and pi are initialized at the const declaration, and their still variables can be seen in the debugger, and their types can be checked as well in the proper manner. Now, these are some of the advantages of const. Particularly, what would you make a const? One is naturally there are natural constants like pi, e, phi, the golden ratio, and so on, or truth value, false value, and so on, or null. If you have used this uppercase NULL, null, to check for null pointer usually, which actually is not anything that the language defines, C language defines. It is actually in the standard library, it is set to, it has a hash defined null to be 0, right? So it has the same problems as the manifest constant. So natural constants are one. The other choice would be any kind of program constants like array size, number of elements, and so on, which makes it very easy to change as the hash define itself. So you must always prefer const over hash define because of these following reasons. The comparison chart is given here. So it can be the main point being that it has type visible to the compiler, can be watched in the debugger, and evaluated only on initialization. So for example, in the case of pi, here if you are using pi, this expression will be replaced everywhere for pi if you did a hash define. So at every point, this expression will have to be evaluated. Whereas if you do a const, then it is evaluated only here, and that value is what is pi initialized with, so that optimizes your program inherently a lot. Okay. Now, naturally, when it comes to pointers, the const-ness take two different meaning. One is because in a pointer there are two variables involved. One is the pointer itself, which is an address variable, and one is the pointed data, which could be of any type. So the question is, what are you putting as const? Is it a pointer to a constant data, or is the pointer itself a constant? So you say either it's a pointer to constant data or it's a const pointer. So here below, I've given an example of when everything is non-constant. Now, suppose you consider this example, pointed data. Int m is initialized as 4. This is non-constant. N is 5, constant, and p is also a pointer which points to a constant data. Right. So it is initialized with ampersand n, the address of n. If you did not have this const here, then this initialization will be a compilation error, because you cannot, as we have already seen, you cannot have a non-constant pointed to a non-constant data point to a constant data, because then with p you can change it. So as you can see here, assigning anything to n is an error, compilation error, assigning anything to the dereferenced version of n, star p is an error. But if you put similarly similarly, if you put the address of m and then try to change this, then it is perfectly okay. Just check carefully that you're pointing to a constant data. So when you take the address could be of a constant data, or it could be of a non-constant data also, because it does not really matter as to if you have to use the pointer to change a non-constant data, because that's always are acceptable. So this is this is this is the kind of things we are seeing in terms of the pointer. Now it is also possible that I can make the pointer constant. I write int star const p. Earlier I wrote const int star p. So const was on this side. Now the const is on the other side. So now what you are saying, p is a constant pointer pointing to a non-constant data. So star p assigned 7 is perfectly okay, because p points to a non-constant data and n is a non-constant variable. But assigning p a different address is an error now. You cannot assign ampersand m to p because it is a constant pointer. So that address cannot be changed. Right? And obviously, by extension, you can have both. You can have a constant pointer pointing to a constant data. So in terms of pointer, there could be 4 possibilities of constness or non-constness. And if you are thinking as to whether if you are feeling a little confused in terms of the syntax, then a simple rule of thumb is think about this star, because it's a pointer, so there will be a star. Draw a vertical line through that. If const is on the right side, on the where you are talking about the pointer variable, then the pointer is constant. If the const is on the left side, that is on the side of the type, then the data that you are pointing to is constant. And naturally, if it is on both, then both are constant. Right? So there are more examples in case of C string. How do you make C strings const and all that? I will not go through every example. You can go through, try running it, and you will get to see the fun. Now, so this is the first lesson that we have learned is we will prefer const over any kind of hash define. Now, along with constness, C++, I mean, in C also we have a notion of volatile data. So you will see that I have given the name here as CV qualifier. It's called const volatile qualifier, the const keyword or the volatile keyword. So what is the notion of volatile? Is the fact that if you think about a normal variable which is not volatile, then you can do read write to a variable. If you write to a variable and then read it, you will get the value that you had written. If you write it again, the value will change, but from the last write to all possible subsequent reads, the value of a variable does not change. That is, the value remains persistent. If you do a const, then you have to initialize the variable with a value which you cannot write. You can only read, right? So it becomes read only. Volatile is an interesting concept where a value of a variable may be different every time it is read, even though you have not written anything. You have not made any assignment directly, indirectly to it. But every time you read, the value of the variable can potentially change. So those variables are marked as volatile variables. So this is in contrast to normal variable which are persistent. Here the value as if is volatile. It is evaporating in thin air from that last time you read, and the next time you read it may be a different value. So just to give you an example, here is a pathological program code in C where you say the function uses the static variable I initializes it to 0 and checking. So this clearly is an infinite loop because every time it initializes to 0 and check for 100. So this will go on for that. So what happens with this when you put it to the compiler? The compiler is intelligent enough to see that I is a constant 0 here. So it replaces I in the while loop condition. So this expression becomes I not equal to 100, 0 not equal to 100. And then the compiler says, okay, I have an expression where everything is a constant, and it does what is called a constant folding, that it is evaluates this expression right at the time of compilation statically. So if you evaluate this, then it becomes true. So the compiler actually, the code that it actually you get is while one, right? It has no existence of I anymore. It's keeps the same semantics. It remains infinite loop and so on. Now you make a little change for this static variable. You write static volatile int I. If you do that, then the compiler will not optimize. The compiler will leave that constant folding or constant propagation and constant folding right there, and this condition will remain. So what is the situation where you will use this is when I can be changed by the hardware at any point of time, right? So often variables in a program not only represents memory locations, they could also represent IO ports, input output ports. So here you are writing a code where you have actually mapped to a port of the processor where some data is periodically coming. So what you are doing, you are infinitely waiting here to see when the value 100 comes to that port. So you are kind of a blocking code, but as soon as you give value 100 in the port, it will start moving. So this kind of features are very required for doing systems programming, particularly our all devices go through port. So there is a sniffer like this in the code which keeps on shaking, and as soon as there is something meaningful happening at that port, then it stops sniping and goes out and takes the action. So here is once you make it a volatile, it is the fact that you have assigned I to 0 is not taken into cognizance. It is potentially that I can actually get a different value. Now, so this was about the CV qualifier. Now we'll move on, and we will take a look at the other use of hash define, which is to use it as a macro. So I'm sure you have done a lot of macros in C programming. This is just a macro to show that you have square. So what again the C preprocessor does? It takes the expression of the macro and replaces wherever the macro has happened with the actual parameter. So if you have written square A, then actual expression that you get to see is A star A. So again, the compiler does not get to see square because CPP has stripped it. CPP has replaced this expression. Compiler does not even know that you had done a macro, right? So, but it has. Then the question is, why do we have macros? Why not simply we have a function? Because I could have been a function. The reason is this is a very simple expression, and if I have it as a function, then there is a lot of overhead of calling that function. So the efficiency goes down, efficiency of your program goes down because you are just multiplying a variable with itself. But to get that function call, you have to do so many things. You'll have to put your registers, save your registers in memory, and then jump to the function location, then create its stack frame, then evaluate the expression, then take that return value back, do an indirect jump back to the location, and so on. So for one multiplication, you will possibly do 100 other unnecessary things. So this is excellent in terms of optimization, but it runs a big
Excuse
risk.
me, sir.
Yes, please. Please go ahead. Tell me.
Removing continuously. So can you change that student?
I did not hear you properly.
So can you change the settings such that students can't remove each other? Like have been removed continuously by someone, I don't know.
Showman, are you there? Showman will have to take care of this because he is managing that. It is very unfortunate. So I'll request everyone that don't. I mean, you all are young, but you are not kids. So please don't play this foul on your friends. It is really affecting people. So please don't do it. And I'm requesting Showman and not Showman. I'm sorry. Here, who is that TA? Abhishek, right? Abhishek and Shoptomi to take care of this. Okay, please make sure that you change their status in a way so that one person cannot remove another person. It should only be the owner of the team. Okay.
And so,
Oh,
so,
yes.
in the micros, sir, can we define multi-line functions?
Yes, yes, you can.
So, how?
Multi-line is a textual matter. The
So,
continuation in the next line is two backslashes at the end. At the
oh,
end of
okay.
that line, we have to give two backslash.
So, like,
Right.
if we want to write a Fibonacci sequence, like using my macros, so what will we do? Like, we have to use the semicolons.
I mean, let us not get into that. We can take that up separately because the whole thesis that I'm going to discuss is that we will not use macros, and there's no reason to use macros. Right. So let us get to that point, and then you ask the question. Then it will be easier to understand. Okay.
Okay, sir.
But I understand that macro is like hash defined constant. Macro is a physical replacement of the code. Right. So this is so compiler does not see it as a function. So actually, if you have a long code as a macro, then your bigger difficulty is you might get into syntax issues because that code is physically replaced at the point where that macro is invoked. One issue. The other issue is that function the compiler has not seen that function, so you cannot debug into that function. We have to always remember these things, that it is just not getting the logic right, but you have to get the quality right. If the
Okay.
code should be such that it is easy to read, easy to understand, easy to debug, and is efficient, only then you have made a good code. Right. So let's look at this discussion. Otherwise, this is what the macro does. What happened? Okay. Now, what is a pitfall? This was done in your PDS course, I'm pretty sure. That if you have defined a macro x star x and you are a later developer in the program, so you do not know what is the definition that is there. So you think you do not know whether it's a macro or a function because it looks the same. So now you call it as a plus 1. Now you expect a plus 1 to be squared. So you would expect that a being 3, this is 4, it's 4 squared, which should be 16. But what will actually happen? This a plus 1 will be replaced for x. So this is the expression. B is assigned to a plus 1 into a plus 1. So you get 3 plus 3 plus 1, 7 instead of 16. Right? So this is a pitfall. And C programmers know how to get around this. So they will put a parenthesis around this so that whenever it is replaced, it is properly parenthesized and it works. Right? So it seems that, well, this pitfall has been taken care of. Now that same developer uses a square for plus plus a. So what you want is a, this 3 plus plus a is a pre-increment, make it 4, and then you square it, so you get 16. But you in reality you will get 25 because this is with the parenthesis, this is the expression that you have got. So you have two pre-expressions, two pre-increments on 3. So it gets to 4, gets to 5, and then 5 is multiplied with 5, you get 25. Right? There's no easy fix for this. This pitfall will remain. I mean, it's you cannot write the macro in a easily in a way so that you can make this plus plus a happen only once, which is what you meant, thinking that square is a function. Right? So that's a big issue. So that's the reason one of the reasons that you won't use macros. So C++ gives you the feature called known as inline function. They are just like any other function, except that you put a inline keyword in front of the function name. Now, what the compiler does is if you declare a function to be inline, compiler tries to put the compiled code of that function at the point of function call. So the whole overhead of function call will get removed. Now the question obviously is, okay, let's look at examples and then we'll come to the question of what can be inlined. So you define the function. So instead of hash define as a macro, you now define it as a function, int square, int x, this, and you write inline. So when the preprocessor works, in this case, it will replace it by a star a. In this case, it will not replace because it's a function. So the compiler will get to see it. Compiler will be able to check the type for the input as well as output parameters, none of which was possible with the macro. And the compiler would retain it in the symbol table so that the debugger would be able to see this. He'll be able to debug. And all these pitfalls, square a plus 1, square plus a, all of these will now be fine because it's truly a function, but it gives you the same efficiency as macro does. And it can check for type. Well, so this is a quick comparison. Naturally, it's expanded. Both are expanded at the place of call, but in macro, it is done textually by the C preprocessor. In inline function, it is done by the compiler after all compilation has been done at the assembly level. Both are equally efficient in execution. Both will make your code bloat. It will make the code bigger. Now, this is since it's coming in this comparison. Just let us understand that we never actually bother about the size of the code. I'm sure none of you probably has ever checked how big is your a.out or whatever exe that you have created. You just don't care. I mean, it's too small compared to the hardware size that, the hard disk size that you have. But it matters severely when you do embedded programming. It matters severely when you write programs for, say, your mobile phone, because mobile phone has a limited space, a limited memory, and data as well as this executable code both reside there. So the code footprint becomes a big issue in terms of all storage constraint programming situations. So code bloat is an issue. So it is not that. So when you make decision, it is not that you write all functions as inline. I mean, that would have given you maximum efficiency, but no, because it will bloat the code. So if you are working in a constrained manner, then you need to decide which function is really important to be inline. I mean, at least make that choice. So these are the other things. Now, the main question is, if you inline every function, will it actually work? Will the compiler actually inline everything? Compiler also makes a judgment. It is very smart these days. So if you inline, say that if this function is inline, the compiler will try to inline, but it may or may not inline. It will see whether inlining actually gives a benefit, because if it sees that inlining is not beneficial in the sense that the code is really, really big and complex, it will choose not to inline, just ignore your directive. Also, if a function is recursive, then it will not be inlined. You can see it very easily, because if you have a recursive function, please mute. If you have a recursive function, like say factorial, then you are calling factorial 5, and before factorial 5 has been computed, you call factorial 4. Before that has happened, you call factorial 3, factorial 2, factorial 1, factorial 0, which is defined to be 1, and then you come back in all these calls. So all these stack frames are stacked with different values of the variable of the parameter of factorial. Now, if you inline the code, you will not have arbitrarily large number of variables to get this effect that you can get in terms of stacking the stack frames of different calls. So inlining will never work. I mean, you can, there's nothing wrong in your writing. You can write a function as inline if it is recursive, but the compiler will never inline that, because the whole concept of macro or inlining, that is replacing the fixed code in the place of call, fails if the computation is recursive in nature. So this is, both of them work only for non-recursive code, right? So this is this is the second important improvement over I mean, this is purely a procedural feature, paradigm feature, but this is certainly a big improvement over C in terms of C++. So inlining is a directive. Compiler may not inline functions with large body. Inline functions may not be recursive. Function body is needed for inlining at the time of function call, because if you just have provided a header and you have called that function, naturally that function cannot be inlined while compiling, because the compiler does not know. Because if you have just made a external declaration for a function, then the function is resolved at the linking time. The compilation time, it is just taken as an address. So it cannot replace the code, so compilation is not possible. So therefore, if you are inlining, you must inline the function, write the inline function in the header file, which will have to be, don't put an external declaration in your source file, but put it in a header file and include that header file everywhere. Because if it is used in 3 different source files, then all these 3 source files will need the function body to be available through that header file so that it can inline the function. And obviously, when you do that, you must make sure that inline functions must not have 2 different definitions, because then you'll get into trouble. Okay, so this is what we have discussed till now. Let me pause for a moment and get back to you to see if there are questions.
Excuse me, sir.
Yes.
When we're defining a volatile a variable, what is the point of assigning it when it can read as a different number however, like randomly?
No, there is no point. There is no point. I was just showing the transformation of the code.
Okay, there's no point in assigning.
There is no point in actually assigning anything, because we will actually not assign anything. I was just showing the difference with respect to the original code. Okay. So you saw that I assigned 0 before the while check. That actually is not intended.
Right. Okay.
Right. And it's the reason that probably you did not discuss about volatile in your PDS course. I don't know if it was discussed, though it is available in C. Is the fact that you are doing discussions at an application engineering level, but now you are getting into serious computer science. So you are not learning the language or its use or kind of good development only for application programming. As computer scientists, you are expected to do a lot of systems level programming, actually build different computer science tools, machines, devices, and so on. So it is now critical that you understand all of these. And as you go through your architecture course and the operating system course, you will be able to understand the mapping between the port and the variable. Right, so there are schemes like memory mapped IO. There's a scheme like IO mapped IO, and so on. So that's okay. So any other question? Why are you so popular? Somebody is removing you continuously. I mean, please bear with it in this meeting, because during meeting it cannot be changed. Abhishek and Shoptami will fix this before tomorrow's class. Any other question?
So can you explain the last point of where you said that inlining is not allowed? regarding this, the same function having different parameter lists?
Not different parameters, different definitions. See, you have multiple source files, right? So what you are doing is you are including this source into each of these source files, right? So if you do not do it through a header file, what you could potentially do is you will put the function definition, right? So that will be treated as multiple definition and will have a problem in terms of this, because it is possible that in one source file you have a definition, in another source file you have a different definition. So that is a cause of that's a big pitfall. So the basic requirement is that you put the inline function in a header file and use that header file. So there is, to you, there is only one visible copy of the inline function. To the compiler, there will be multiple copies available, but they are all copies of the same copy that you get to see. That, I mean, these are all programming practices that you must be aware of, and now you know the reason of why we are saying this. Normally, it normally cannot happen with a function. With a non-inline function, this situation cannot happen, because if you write two definitions for the same function without the context of overloading, that is, with the same identical set of parameters, if you have two definitions of the function occurring even in two different compilation units or two different source files, then the linker will give you an error because of multiple definition. This cannot happen. But for inline function, this multiple instances of the definition are required, because otherwise in independent files you cannot inline that function. So for inline functions, this check is ignored, right? And you have to make sure that they are the same definition. And the easy way out is only inline functions must only be written in a single header file, and that header file be included in all the source files which need to call that function, right? So this is more of a programming practice, I would say, which will make sure that you don't insert unnecessary bugs. Okay. Any other question, anybody?
Sir,
Yes.
Sir, can you please accept my invitation for the team?
Pardon?
Can you please accept my invitation for the team? I have sent the invitation for the team. This Microsoft team.
You did not register earlier?
Yeah, no, sir.
Why?
Sir, I was late in registration, so I have sent the invitation.
No, because the process is that we take it from the ERP and said that. What is your name? Okay, today the class is almost over, so it will get added. Please send a mail again and CC Abhishek. Yeah.
Okay, thank you.
So he's actually doing that, so he will get it done. But complete your registration. Today is the last date. Okay.
I have completed it.
Okay. Okay. Then it will, as it is, get done, because at the end of today we will take the fresh list from ERP again and get it done.
Okay, thank you, sir.
Any other question?
Sir, if a function is not defined as inline, can it be inline?
The compiler will not.
Okay, so if I want it to be inline, I must define it as inline, and then it may be inline.
Yes. It is a directive. You are saying that, dear compiler, please inline. Now, it will not be inline. What I said is kind of, take it with a pinch of salt, because inlining is this specific feature where the programmer can direct the compiler or suggest the compiler that this function is worth consideration for inlining. But there are other ways in which a function can disappear in your code. For example, if the compiler finds that a function is actually computing something which is a constant, the compiler might just do that computation and replace that computed value in your code. For example, you saw in case of pi we are defining at 4.0 times arctan 1.0, right? Arctan 1.0. Now arctan 1.0 will always have a constant value. So what the compiler will do in optimization, it will evaluate, it will invoke a10 with 1.0, take that value, multiply it by 4, and replace that value actually. Okay. So that is the reason when you build, you always have two different kinds of build for your program. One which is called the debug build. In a debug build, all these optimizations will not happen. So you will be able to, actually inlining will also not happen. In a debug build, inlining will be stopped so that you can debug and get into that function, step into that function to check if that function is right. But if you do a release build or a production build, which is again given by the compiler, there are two different modes. I mean, if you are doing GCC, it's if you have just compiling, it is a optimization compilation or release compilation. If you do -g, it gives you a debug compilation. Now, if you are doing a release compilation, then it will do all sorts of optimization. So it will inline, it will fold the constant, propagate the constant, so that if you debug a release build code, you will often see that you can see the text of the function in your IDE, but you are not being able to get into that function. Because in the assembly, actually that function call has been removed because of the compiler has optimized it out. Right. So these different gradation, and in fact, in optimization also, in a release build, there are different levels of optimization that many compilers give as to how much you want to optimize. The more and more you optimize, it becomes more efficient, at least from the compiler's perspective. But it gets that much more difficult, because now the situation that you'll get into is you have a code which runs correctly in the debug build and gives you an error in the release build. This is a very common industry problem. So since it gives error in the release build, you have no easy way of debugging it, right? So these are issues which becomes the kind of difficult deterrent. So while building the code or while developing those programs, you have to over time learn that how to write the code so that the big debug and release builds will not behave differently. But in many compilers it does, because of certain things that you have done. That, for example, one very common violation which we will talk about tomorrow is returning a function local variable as a reference, as a function value. So this is something which might work in the debug build, because incidentally that stack frame exists. But in the release build, if the compiler has optimized that function out, then actually the stack frame never existed. So that variable is no more existent. So returning that as a reference will be completely give you some garbage value. So here you see that you have to understand what changes might happen, because the compiler compiles and optimizes things and work accordingly. And that is the reason we are talking about these guidelines as we are learning the language, that, well, never return a temporary variable of a function as a reference. I will talk about that more in tomorrow's class. Today we are completely out of time, so we could just do two of those procedural enhancements in C, which is const-ness, volatile, and the inlining of the functions. Tomorrow I'll talk about references, default parameters, overloading, and all that. Okay, thank you all very much. See you again tomorrow at 8 o'clock. Bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.